think we were doing small and bigger units of length.
Computers will write here.
Parsec.
Parsec.
Okay.
So it's the volume meter.
Huh?
Volume meter.
It's up to you.
So shall I write it from
Volume is like everything is given like in a summary style. Okay, textbook has got more detailed. So volume is more useful when you're doing questions. Okay. Because it includes lots of questions asked in exams and stuff. So it's up to you. Like you can bring both the books, textbook as well as volume. Okay. But I think this parsec etc. is not given in the volume. Is it given? Awesome. Focus here. Focus. Okay. What is parsec? So we discussed astronomical unit. Anybody remembers what is that? What is astronomical unit?
average distance between Earth and Sun?
Correct. So throughout the year, the distance between Earth and Sun changes. So the mean distance between Earth and Sun is called astronomical unit. So let's say this is Sun and this is Earth. So it goes something like this. So this distance you see here is more than less, least, again increases. So you take the mean distance. Whatever is the mean distance, that is called one astronomical unit. And there is some value. Now what is parsec? Now see, if you take this as the base, okay, and from Sun and Earth, let's say this is some point. This point has some distance away, right? So it makes some angle. Let's say theta 1. Right? So now if you go away, let's say here. What is happening to the angle? Is it increasing or decreasing? So angle is decreasing. Okay. So now imagine a point so far away, right? So far away. We don't know. So far away. Where this angle is equal to 1 second. How much is the angle? 1 second. You have an idea what is the relation between 1 second and a degree? So 1 degree has 60 minutes and 1 minute has 60 seconds. Okay? So what is 1 second? Therefore 1 second angle is equal to 1 by 60 minutes. And what is 1 minute? What is 1 minute? 1 by 60 degree. So total 16 means 60. So this is 1 by 3600 of a degree. So 1 second angle is 3600 part of a degree. And how much is 1 degree? You have seen that a protector. That's the smallest angle, right? That smallest angle you divide 3600 parts. It's so small. That angle is 1 second. So which means it is very, very small. This itself is a very large distance, right? How much is 1 astronomical unit? It's of the order of roughly equal to 10 raised to 11 meter. So from such a big line, you are going to so far away that the angle varied is 1 second, very small. Okay. So that distance will be obviously very far, right? So that distance is, and there is also a relation. So this is that distance, this distance. So let's say that distance is d, right? And there is a relation between angle is equal to arc by radius. Okay. So this you can treat as radius, so it will make a very giant circle. And there is a relation between angle, arc and radius that you are going to learn in mathematics. Okay. So this radius is d, right? And that is theta equal to, and arc is 1 astronomical unit, and radius is d. Therefore, this d is equal to 1 astronomical unit divided by what is theta? Theta is 1 second. Okay. So, and then you have to convert this into radian. You get it? Degree has to be converted into radian. 1 minute is 1 by 3600 degree. And how much a degree is in terms of radian? Pi by 180. Okay? So when you do all that conversion, right? So this becomes, this value comes 3.08 into 10 raised to 16. Okay, when you substitute the value of astronomical unit in meter, and we substitute the value of 1 second angle in radian, okay, with appropriate conversion, this is the value. So this d is nothing but 1 parsec. Point 0.08 into 10 raised to 16. So it is roughly equal to slightly more than 3 light years. So this is about 3.26 light years. So it's even bigger than light year. Understood? So parsec is the biggest length unit that is used in astronomical calculations. Distance between galaxies or distance of stars, those kind of things. Okay? Understood? Yeah. So don't worry too much about how you're calculating. Nobody is going to ask you about it. Just know that this is some large length. Okay. Likewise, we have certain smaller lengths, right? Smaller length. So have you understood what is parsec? Read what is given in the book. There's a definition. 1 parsec is the distance from where the semi-major axis of the orbit of Earth, which is 1 astronomical unit, subtends an angle of 1 second. So what is semi-major axis? See, in ellipse you have 2 axes. This is called major axis and this is called minor axis. So major axis, half is called semi-major. That half is 1 astronomical. Okay? That distance is 1 astronomical. Got it? Yeah. Chalo. Now let us discuss smaller units of length. So what are the smaller units of length? So obviously you have centimeter, which is how much? 100th of meter, or 10 raised to minus 2. Okay, standard is 1 meter, and the smaller length is centimeter. You also have millimeter. So 1 centimeter. It's written as 1 cm. Millimeter. You write 1 millimeter. Here you can write that is 1 centimeter. This is equal to. So what is 1 millimeter? It is 1,000th part of a meter. Or 10 raised to minus 3. Okay, so when you keep dividing the length in smaller parts, then you also have micrometer. This is written as, this is read as mu or micro. Okay, the symbol is mu. M-E-W, mu. Or MU. Okay, but MU you may read as mu or Mumbai may just MU there. So this is how it is pronounced. And what is it? It is 1 upon. So it is 1 millionth part of a meter. 1 by 10 lakh. Okay. So when you divide 1 meter into 10 lakh parts, one part is micrometer. So very small length. Okay. You have even smaller lengths than this, which is 1 angstrom. Yes.
Where is this micrometer used?
Like thickness of hair or radius, or there are certain nerves which are very thin, nerves in the eyes. So there are like
Plastic bag on the
yeah,
plastic
even
bag
plus
also.
yes, it is very thin.
This is
The thickness of the plastic.
Is it?
It is also called as micron. Micrometer, micro is short form for micron. Micron, micro, mu, one and the same. Okay, so there are very small lengths also. Now we are going to even smaller length, which is angstrom. How much is this? It's written as 1 angstrom, and this is equal to 10 raised to minus 10. It is 10,000 times smaller than a micrometer. Okay, so it is 10,000 times smaller than even that. So this is the size of the atom. The diameter or radius of the atom is roughly this much. Okay. So this is yes, atom. Can you see it with naked eyes? No. So this is what it is. Okay. Comparable size of atom. So the atomic sizes are of the order of angstrom unit. And we also use this unit to express the wavelength of light. Light has one property called wavelength. Okay, so we are going to study about it. So wavelength of light is in terms of thousands of angstrom. Like the visible light, white light. White light has 7 colors into it. Okay, so if you go from violet to red, right? So the range is from 4,000 to 7,000 angstrom, 4 to 8,000 angstrom roughly.
Like you have to zoom that way.
Huh?
You have to zoom that is to see the different colors.
Yes, exactly. But you can't see it like you can't measure it. You require theoretical calculation. So all these smaller lengths. So for measuring it directly, like you can measure a meter through an instrument directly, but the instrument to measure these kind of lengths are very difficult. Now we have electron microscope, etc., where you can measure such small length. But when they were not there, you have to use theoretical calculations. So you calculate it, right? Like how can you measure parsec? Can you measure parsec? No. So we have arrived at this number through theoretical calculation. Some principles of trigonometry, etc. Okay, so this is called indirect measurement. When you can measure the length directly, or when you can measure the quantity directly with the help of instrument, it is called direct measurement. But in science, your senses are very limited. Okay, so what we cannot measure directly, we have to rely on calculations. So That is called indirect measurement. So these things have been experienced by scientists. Okay, so I'm just making you familiar what are different types of smaller lengths, right? Because anyway in biology you'll be coming across bacteria and atoms, okay, molecules. So those sizes are very small. Even smaller lengths are like picometer. Picometer. So 10 raised to minus 12. So is there any end to it? If you can keep on going partitions, you will arrive at smaller and smaller lengths, right? So whatever length is known or experienced, so we are going to mention that. Do you have smaller length than this? For me. So which is Fermi, or it is also called femtometer. 1 femtometer. So it is like written differently. 1 Fermi or 1 femtometer is the same thing. That is 1 mm, which is 10 raised to minus 15 meter. This is comparable to the nuclear dimension. Inside atom you have a nucleus. So nucleus is almost 1 lakh times smaller than the atomic size. Okay, like if you take the atomic size as a room, then nuclear size will be like a head of the pin. Head of the pin head, obviously. So most of the atom is empty space. So we'll read about it. Have you read about Rutherford experiment?
Yeah.
Yes. Yes, worldwide. So the nuclear size is like very small as compared to the atomic size, but yet the entire mass of the atom sits inside nucleus. So although it is very small, but it's very dense. Okay, so all the mass of the atom is inside the nucleus. So the nuclear dimension is Fermi. So that's small. Okay, so are you getting the idea? So just like lengths, we have. So there is a summary given in your book. This table is given. So sometimes some memory-based questions are asked, but now the questions are getting more application-oriented. So less and less questions from memory may come. But still in class test, they might ask you how much meter is a parsec. Okay, so when you solve numerical sum, few things you may have to memorize. So try to remember the order. It's hard. I have difficulty remembering. Okay, but with practice you may. Right. So the order is like 10 raised to 11 meter, then parsec is 10 raised to 16, and this is 10 raised to 11, right? Light year is how much? Uh, Light year is roughly 10 raised to 15 meter. 10 raised to 15 meter. Okay. 9.46 into 10 raised to 15. Order.
Meter or kilometer?
Meter. Just before that it is meter, 10 raised to 15. Kilometer is 10 raised to 12.
Yeah.
So divided by 1000. Okay. So remember it in meter. So in table everything is given in meter. So just focus here. There are so many extra things given. You're not expected to. Nobody is expecting you to memorize all that. Not possible for anybody. Okay. So the only the few which are important ones are given in the table as a summary. So just focus here. Now we'll move on to mass units. So any questions here? 10 units. So let's go to mass units. So mass also has bigger and smaller units. So mass units. So SI unit of mass is kilogram. Okay, this is. But there are many masses which are very small. Like what is the mass of the atom? Atomic mass unit, which is how much? So small mass units. So first we'll see small mass in metric system, like 1 gram. How much is 1 gram? 1 gram is 1000 part of kilogram. Okay, that is 10 raised to minus 3 kilogram. 1 gram is 1000 grams. Likewise, you have 1 milligram. So when you put some prefixes, then 1 milligram will be 1000 part of this 1 gram.
Oh, yeah.
It is 1000 of a gram. So how much is this now?
10 raised to minus
Then 1 gram is this. So this will be 10 raised to minus 6 kg.
We need a gram or kg?
Standard unit is kg. So any smaller unit has to relate to kilogram. Likewise, you can have microgram. You can go on all those prefixes. Right? So then you have some non-metric units. Like you don't use meter or kilogram or second, right? I mean, second has to be not meter or kilogram. So here, what do you have? Mass of the atom, one atomic mass unit, or it is also called unified mass unit. One EMU, atomic mass unit, or unified mass unit, same thing. And this is equal to what is how it is defined? It is 1/12 of the mass of C12 atom. Carbon has different isotopes. So which isotope? C12. Carbon is available as C14 also. Right? So it is 1/12 of C12. 1/12 of mass of C12 atom. Okay. This is how it is. So what is 1/12 of mass of C12 atom? Now you have to apply here the mole concept. What was the mole concept? Do you remember the mole concept? I told you, like 6.022.
1 mole of any substance is its atomic weight.
Correct. So if I take 6.022 into 10 raised to 23 carbon atoms, okay, it will weigh 12 gram. Understood? So I will use that logic now by unitary method. So when I solve it, this is 1/12 into this will be 12 divided by this is 12 gram for 6.022 into 10 raised to 23. Okay. So 12 you have to multiply. It is gram, so put it in kg. It will be 10 raised to minus 3 kg, right? So 1/12 of this. Okay. So how much this becomes? When you solve this, you will get 1.67 into 10 raised to minus 27 kg. This is what you will. ठीक है? मोल कॉन्सेप्ट से हमको क्या मिलता है? जो मॉलिक्यूलर वेट है एटम का, वो ग्राम में मिल जाता है और 1 मोल ऑफ C12 है. Okay?
6.022 to 10 raised to the power of 20.
So this is the conclusion by all the scientists. The finding is it is called Avogadro's constant. So this has been arrived at by various experiments. We just use that known data. It's like once you know that wheel is required to run the car, right? So we just use it, right? When we design car, we don't reinvent the wheel. Okay, it's the result. It is the finding of the scientist. The person who gave this is known as Avogadro. Okay, Avogadro's constant. It is also called as Avogadro's constant. And these many bunch of anything atom molecule is called a mole. The group of these many species, either atom, molecule, anything is called a mole. Is that clear?
So it is finally pick carbon, like C12.
Why carbon? Because it is the most abundant substance in the universe. It is found in both living and dead entities. Okay? It is part of both living and non-living thing. Are we not exhaling carbon all the time? So where is it coming out from us?
From our lungs.
So even if we are dead, we will have some carbon in us. That's how they do carbon dating. It is also in the rocks. So they find out how many millions of years old it is. Fossils inside. Okay. So carbon is, so you have carbon, nitrogen. These are, very essential elements of all beings, living or non-living. Okay. So that's why we've settled for carbon. So this chapter is the entire physics that you can learn going forward till your doctorate. Units and measurements. Avogadro's constant. Avogadro. Will you read your book? Read book. Everything is given. When you read about mole, it's given here. Okay. You see here, it's given in the footnote. Avogadro's number. So read book. Find somewhere. My book may have a different value. Below the units of mass, that footnote. See the footnote. The footnote is in the foot. Footnote is in the foot. Okay. Now, so have you understood? So likewise, we have this is non-metric. We have another non-metric unit which is solar mass. Now we go to the bigger units. So here we have defined some small, and you can go further small also by using different prefixes. Bigger units may have bigger non-metric unit is solar mass. Solar mass is of the order of roughly 2 into 10 raised to 30 kilogram. This is the mass of the sun. Somebody weighed sun on a physical balance. It has been theoretically arrived at. Okay, using Newton's law of gravity. So anything that we cannot measure directly, we have to theoretically calculate it. Okay, so because if the principle is valid for small masses, that we can do in our laboratory. So the same thing can be applied to bigger masses. That is called logical deduction. That's how science progresses. If it works in a test environment, then it should also work for other things. That's how we indirectly measure it. So where do we use this? Again, we use it for planetary calculations. Whenever we are dealing with heavenly bodies, etc. That's when we use how many solar mass is that planet. Okay. Things like that. Okay. So as you know that unit measurement is done by comparison. And what do we compare? We compare the parameter against some unit. So how many times of the present unit? Okay, that is what gives you the measurement. The measurement is all about comparison. Okay, so with this we have covered all the small units of mass. Let's do the bigger units of mass. So bigger units of mass is 100 kg and 1000 kg, which is 100 kg is called quintal. Mass. So 100 kg equal to 1 quintal. And 1000 kg is
Done.
1 metric ton. Okay, sometimes it is just written as KOL. So this is 1000 kg. So everything we have compared with kg, but what is 1 kilogram? Nobody asked me. We have to know na, how much mass is 1 kilogram. So this is a reference mass kept at Paris, 1889 में एक cylinder है metal का, platinum iridium cylinder,
Like the road.
like the rod. So that mass is accepted as 1 kilogram. Okay, and then its replica or copies, its clones have been circulated throughout the world with every bureau of weights and measurements of respective metals. Right. So, but that was in old times. Now there's a different standard adopted, and you need not worry about it. It is measured in terms of Planck's constant. You are yet to know what is Planck's constant, right? Max Planck, some scientist, peer of Einstein and all. These people are. So there is a different standard for a kilogram. So don't worry about it. Imagine that you know what mass is 1 kg and everything is built upon. Okay. So if you read the book, it says in 1889, 1 kilogram was defined as the mass of a cylindrical piece of platinum iridium alloy kept at International Bureau of Weights and Measures at Cyprus near Paris. Okay? So people sit down, sit together and decide, okay, we will call this 1 kg and then the whole world follows it. Okay? So that's why. And the whole world has to follow it because a kg here should be a kg in UK or England, right? A meter here should be the same meter in any other country or in space or inside sea, anywhere. Okay, so that's why it is standard. Okay, fixed. Once decided, no deviation now. So, like length units, you also have a summary of all the mass units. So, these are important ones. Okay, so just try to memorize it. Then we will move on to the units of time. Time. So of course, the SI unit you know is second. So time is duration. So what duration is 1 second? What is 1 second? So we time between these two ticks. Is it 1 second or 2 seconds? So I may not be perfect in producing the ticks, and between my two ticks, the duration may be different, and each of you may have a different. So that cannot be a standard duration, right? So to measure time, we have to find out some natural phenomena which repeats itself after fixed interval. Correct? Only then we can say, okay, this is some time duration. So what comes to your mind? Sunrise, time interval between two sunrises and the next sunrise, right? So what is happening? Earth is spinning on its axis, okay? So it is spinning at a constant speed, right? So the duration of two sunrises must be taken as a constant. Is it constant? Throughout the year? It's not. So that's why it is the duration is called as mean solar day. Throughout the year, you measure the duration between two sunrises, right? And then take the average of it. So that is called mean solar day. So how do you define 1 second? 1 second is equal to 1 divided by, so each, so 1 mean solar day. One mean solar day is the time duration for rotation of Earth over its axis, or time between two sunrises in solar. Now we have divided this duration into 24 parts. Each part is called an hour. Okay, one mean solar day has 24 hours. Each hour is also divided into 60 parts, which is called minutes. And this is then divided into 60 parts. So when you do all this, okay, so mean solar. So this you get as Yadavi Avanavi. So all this now gets converted into 1 second. So this is 1 divided by 86,400 part of a mean solar day. Okay. Whatever is the time interval between two sunrises, when you divide that time interval into 86,400 parts, one part is second. Then old days, this was the standard for a second. So like I said, we have to find events which occur at the same duration. But in case of solar day, this is not consistent. Keeps changing, right? So now we have atomic clocks. Okay? So there is an atom called cesium. Cesium 133. Okay? So it has energy states. Right? Every atom has got an energy state. So higher and lower energy states are there. Right? So whenever this atom switches from one energy state to the other energy state, it emits radiation. What does it do? It emits radiation. So these radiations are emitted in the form of electromagnetic radiation, electromagnetic wave, right? So this is one wave cycle. So wave consists of wave cycle. So it is 2, 3 like that. So this has got a fixed time period. Each wave cycle has a fixed time interval. Okay. So what is taken as 1 second is 1 second is equal to, now this you can count 1, 2, 3. Okay. This cycle is also called as vibration. 1 vibration, 2 vibration, 3 vibration. Right. So when this cesium 133 atom emits 9192631770. This corresponds to 9192631770. So when the cesium atom emits, releases these many vibrations, it releases very fast. So that duration is called 1 second. Now imagine how fast it is emitting. Can you read this number? What it is?
91,631,700.
Whatever it is. So many vibrations are emitted in such a small duration. Okay. Now this is the most accurate clock, the atomic clock. Understood? So because this is repeatedly causing some event. So vibration is a repetitive event. Right? So you need not remember all this. I'm just telling you that what a standard second duration means. So it has to be after certain event which repeats itself. Now, so we are going to do all this when we discuss the oscillations and pendulum. It is also called vibration. This is called cycle, one vibration, or one oscillation. These are all one and the same thing. So having known what duration is second, there are certain events which take place even at a smaller duration than this. And you have millisecond, microsecond, okay, all those things are there. And certain phenomena will be like bigger than it, bigger than this. So second से बड़ा क्या है? Minute, hour, days, year. So these are durations. Then 10 year is a decade, correct? So year से भी पहले you have month. Months also you have lunar month and month as per English calendar, which is Gregorian calendar. So these are so many, different bigger units of time. So smaller units of time. I forgot to tell you one small length, nanometer. That is 10 raised to minus 9. So it will come here. So you have millisecond. Millisecond, which is written as 1 ms, which is 1000 part of a second. Then you have microsecond. So again, these are the familiar prefixes. Okay. Then you have, there is one shake also. Shake, SHAKE, which is one shake. Is equal to 10 raised to minus 8 second. I don't know what this means. Is it like when you're shaking something, that duration? Or what is it? 10 raised to minus 8. Okay. So it says shake. Then you have 1 nanosecond. And raised to minus 9 second. So these things will, get stored in your memory. In atomic world, etc. Okay, you're going to use all this. Except shake, I have not used shake anymore. But millisecond, microsecond, nanosecond, etc. All these things you are going to use. Then bigger units of time. So you have minute, 60 seconds, you have hour, 60 minutes. So you have a day, which is 24 hours. Right? Units are generally not written as plural, okay? It's just written as singular. Unit is singular. Then you have month. So month, some days are like 31 days, combination of 31 days, 30 days, and 28 days, and 29 days. Only February has 28 or 29, so it depends. So this is a month, right? Then you have year, which consists of 12 months. These are different months, different days. But on an average, it is taken as 30 days. Right? So 1 year is 365 days. Actually, it is yes 365.25 approximately. So, like every fourth year, 1 day becomes extra. That on that fourth year, the Feb month has got 29 days. Otherwise, it is 20. Okay. So then you have 10 years is called a decade. Years. Then 1 century, 100 years, 1 millennia, called 1000. Okay. So this is all about the first part of units and measurement.
So there is a PNC.
Huh?
Second,
Yes, we are going to do. Because here, whatever school, okay, we teach the full syllabus. Would you like to learn the full syllabus? Would you like to learn the full syllabus, or what your school leaves you, you also want to leave? That's why I paid money for it. Because here when we take class test, so the questions will come from that full syllabus. Unless you have learned, how will you answer it? Okay. So in schools, things which are slightly tricky or difficult, they keep it for the last moment. And then by the year end, the last moment never arrives. Okay, that's what. So we'll do it later, that later never comes. This has been our experience. Okay, so
so
yes,
in one microsecond is one μs, right? Or
yes, μs. Micro is mu everywhere, irrespective of length, mass, or time. It's a prefix, standard prefix. So it's a multiplier. So I hope you got fair amount of ideas in how to deal with units and where to apply it, to what quantities. You have fundamental quantities and derived quantities. Okay, and what are the units and how to use it. You'll become more comfortable when we do something like this. All that I have discussed here will be useful for your chemistry also. Because there also you'll have some chapter on units and measurement, I guess. But mostly around mole concept. Okay. Now, precautions to be taken in selecting units. Did we discuss it? What precautions to be taken for selecting choice of units? Choice of units. So how should we choose unit? It should be easily available, right? Like तुम्हारा जो scale है, measuring instrument है, it should be easily available in the market. Easily available means unit should be reproducible. First of all, it should be of convenient size. It should be of convenient size. Like if you want to take direct measurement, the instrument should be convenient. Okay? Like scale को तुम इतना बड़ा कर दो कि लेके रूम में नहीं घुस पा रहे, ऐसा नहीं होना चाहिए. So it should be of convenient size. Then second, you have it should be possible to define the unit without any ambiguity. Right? It should be non-ambiguous. Non-ambiguous means it should be clear. Right? The definition should be very, very clear. There should be no confusion in it. Then it should be easily reproducible. is the meaning of it? Let us say your instrument becomes old or lost, then will you not be able to measure anymore? You can, right? It should be easily reproducible or available. Right? 4. It should not change. It should not change with space and time. Okay. So the length which is 1 meter today should remain 1 meter tomorrow also. Right? I mean, the length should not increase or decrease. It should remain same. And also, if it is 1 meter in India, the same length should be 1 meter anywhere else in the world. Okay? So it should be independent of space and time. Clear? So that's what is given. It should remain same everywhere. Now we can do some numericals. So there are some 7 numericals given in your textbook.
So, that is ambiguous.
Ambiguous means not clear. So it should be non-ambiguous, it should be clear. Confusing. Or confusing. Not be confusing. So there are so many objective types, multiple choice questions and all that you can do yourself. Okay? Because all the theory that I have taught, you should be able to answer. We'll do some numericals. So there are 7 numericals in my book. How many are there in yours? 7. Okay. So let's do the numericals. Correct. So I will take up alternate numericals. So the one which I do not do is homework for you. The one which I do is classwork. Okay. And while doing homework, if you're stuck anywhere, you can ask for help in the next class. Is that okay? So there are 7 numericals. So generally I decide odd or even, depending upon the last number. The last number is odd, I do odd even. The last is even, I do either even or odd. Okay, so what is given? What is the first numerical in your book?
The wavelength of light of a particular color is 5800 angstrom explicit in nanometers.
So what is wavelength? This length, this distance traveled by one wave is called a wavelength, and it is written as lambda. Okay, lambda. It represents wavelength. So wavelength is the distance traveled by the wave during one cycle. Okay. So what is the distance traveled by the wave in one cycle? It is given as 5800 angstrom. Lambda is equal to 5800 angstrom. So how much it is in meters? 10 raised to minus 10 meter. Okay. So this is what you should do. Express it in nanometer and meter. So meters I have already expressed. So how much it will be? So you can take 3 powers back. So it is 5.8 into 10 raised to minus 7 meter. This answers part B of the question. Okay. So part A में you have to express it as nanometer. So what is a nanometer? Minus 9. So you can just separate it. So since 5800 angstrom is equal to 5800 into 10 raised to minus 1 into 10 raised to minus 9 meter. Now this is a nanometer, so you can write it as 580 nanometer.
So in the first part, the upper one, we have to convert it to meter, nanometer.
Nanometer, yes, in the
So
first
the
part.
upper one.
No, that I just wrote. You can, if you don't want, you can just remove it here. Okay, write it over here. So you can write it in two parts. सबसे पहले तो एंगस्ट्रॉम को लिखो 10 raised to minus 10 meter. This is in meter. Then you can write 5800 into 10 raised to minus 1 into 10 raised to minus 9 meter. But what is 10 raised to minus 9 meter? It is nano. And this 10 raised to minus 1, you will cut 1 0 here. Okay? Are you familiar with calculations of power and exponent? So what is it? Minus 10 can be written as minus 1, minus 9. And we have split the base. Everybody understood? This is what it is. And the second part is in meters, so you can express it yourself. So P 5800 strong is equal to 5800 into 10 raised to minus 10 meter. So now in the book the answer is given like this, so hope you understand how it came.
Yeah.
3 zeros, close it. So this is in meter. Okay. Shall we do one more question or will we stop here? Okay, we'll do in the next class.
So
Oh.
can we express it as 58 into 10 raised to minus 8?
58 into
10 raised to minus 8.
generally the good practice is this. You write the decimal after the first number. This is the scientific expression.
So it's not.
First number, okay, has this and then the power of 10.
So you have to put
Here
it-
also, since it has to be expressed in nanometer, therefore we wrote all this. But in meter, this is how. This is called scientific expression. All right.
No, not like that. No. Wait, wait. Yeah.